All right, it's already 10:34, so I think we should get started anyway. All right, welcome to week 14 of AI504. So this week we're going to talk about graph neural networks, GNN. The table of contents is like this. So we're going to first talk about graphs for those of you who are not familiar with graphs, the definition of graphs. So for those of you, it'll be just an opportunity for a recap. And then we're going to talk about graph convolution. And then we're going to move on to the relationship between graph neural networks and transformers. So more specifically, we're going to talk about the relationship between self-attention and graph convolution and how they're related and how recent model architectures exploit this relationship. All right. So graphs. Those of you who took the class of data structure or algorithm will be already super familiar with graphs, but those of you who are not, who didn't study computer science as an undergrad, or who's has not taken data structure, please pay close attention to what graphs are, because it'll be just a high level overview. So graphs are data that consists of all kinds of data that consists of nodes and edges. So nodes are, this clear diagram shows what a graph is. So this graph has nodes like A, B, C, D. So all the circles in this picture, in this figure, are nodes, and all the lines between a pair of nodes. So here there are lines between C and D, line between H and F, line between B and C. They are called edges. And they both nodes and edges have different names. So nodes are sometimes called vertices. So a single node will be a vertex, and a group of nodes will be called vertices. And edges are sometimes called relations. Oh, there's a typo, actually. It should be relations. So, and there can be many variations of graphs. So nodes can have either node-specific features or not. So we'll talk about this, but for example, when we move on to social networks, we'll talk about the node-specific features. So each node can have its own features or not, and edges could be undirected or directed. So here in this graph, in this figure, there is no direction because there is no arrow here, right? There's no arrow. So it's just whether a pair of nodes is connected or not. So whether there is a connection or not, it's just binary relation. So there is no direction of connection. And there is also, sometimes there can be multiple relationship types or not. So here, the relations are, it's just a relation. It's just whether H and F are connected or not, whether I and F are connected, or whether a pair of nodes are connected or not. That's the only relation types or edge type. But sometimes there can be multiple types. We'll also talk about this when we get to knowledge graphs, right? So so there are many data sets that can be seen as graphs. Actually, any data can be seen as graph, but we'll talk about this. But typical graph data are Facebook friends, web documents, road networks, chemical compounds, knowledge graphs, knowledge bases. So we'll take a look at them one by one. So friend networks, there are, for example, we can think about friend networks from Instagram or Facebook or Twitter or something like that. I don't know any more popular social networks, but for example, let's start with Facebook. So when you're using Facebook, there are about, how many people? There are about 1 billion to 2 billion users in Facebook all around the world, and each user will be a node. So here, this is just a subgraph of the Facebook friends, for example, and each node or each circle will be a single user, and each user will be friends with some other users. And obviously, it will be a very, very sparse graph, because if you think about the number of users in Facebook, for example, let's say that there are 1 billion users, 10억이죠, 1 billion users in Facebook. Not all of them will be friends with everybody else. So for example, we're typically friends with maybe 100 people or maybe 200 people, but there are 1 billion users in the world. So this graph will be extremely sparsely connected. So, and we're just taking a look at a subgraph. So there are about 15 users in this graph. And in Facebook, when you're friends with someone, that friend is also friends with you. So you can't be, there is no direction. So when you're, for example, when A is friends with E, they are both friends. So it's undirected, or you can think of them as bidirectional, but typically you're called just in this case we just call them undirected. So when you're connected, you're just connected. But if you think about Twitter, you can follow someone, and that person would sometimes that person follows you, or they don't follow you. So there is a direction. There's a direction in Twitter networks, because you follow someone, but that person might or might not follow you back. So in that case, it's directed. But in Facebook friend networks, there's no direction. It's undirected. And typically the nodes are unspecific. So it doesn't matter whether it's M or G or H or K or D. There is no feature whatsoever. We just index them so that we can distinguish between different nodes, but it doesn't mean that each node has any specific features. We can use feature. For example, if we go into more detail, if we stick to the Facebook example, each user will have a certain age, a certain gender, a certain job, certain geographic location, certain posts that they uploaded. So in that case, you can use them as features. But typically, when we use friends network, like Twitter network or Facebook network, we just we typically treat each node as unspecific, just empty node, and you're simply just interested in whether something, how the graph topology looks like, the structure of the graph overall. Right, and back in the early 2010, 2009, late 2000 and early 2010, when Facebook was the thing, when Facebook was really popular, when it first came out, analyzing their network was a super interesting task. So that it was called social network analysis, SNA. And typically what you would do is you would find influencers who are most connected to other people, or who you should target if you want to run an advertisement. If you're like an advertiser and you want to pay someone to use your product, for example, if you're a pharmaceutical company, or if you're a makeup company, you want to send free products to certain users, and you can't send free products to all the users in the world. You have to target some number of users, and that user should be like an influencer, in that domain, in the makeup domain. So when you give them free products and they use your product, then it will maximize the advertisement effect. So that's finding the hot influencers. Also, recommending friends, back in the day when you were using Facebook, it was almost like it was as if they knew your friends already when they recommended friends. Do you know this person as a friend? They would ask that kind of question when you first started using Facebook, and it was so accurate. And that was all based on graph analysis or social network analysis. And these days, social network analysis is still a really heavily used technique or technology for example, in Instagram or Twitter, for advertisement. Is still a very hot topic, right? And Google's PageRank, if you know about PageRank, then you will already know that they are using internet. If they're treating internet as a graph consisting of documents, web documents. So if you don't know what PageRank is, PageRank is an algorithm that the founders of Google came up with when they were trying to build a search engine basically. So when you're building a search engine on the internet, your search engine should accept as an input a keyword, a short query. It could be like okay, I'm just gonna mute everybody. So the query could be anything. It could be a food or like movies or whatever interested. And your engine should accept the query and then return a list of documents. And that list of documents should be ordered in a way that the first document should be the most relevant document to your query. So that should be the spec of your search engine. And there can be infinite different ways to sort, basically come up with a list of documents, sorting the documents. And the algorithm that the founders of Google, Larry Page and Sergey Brin, came up with is PageRank. So I guess like Larry Page spent a little more time on coming up with the algorithm compared to Sergey Brin. So it's called PageRank, and the way they do it is they treat the internet as a graph consisting of documents. So each node can be seen as each document, each web page, for example, a single web page, like a .html or whatever, a single HTML will be a single node, and a link. There can be links inside a web page, right? It could be external link. When you click, you go to the page, right? So that link is those links are the relations or edges between nodes. So in this case, the nodes will be still documents. So the edges or the relations that connects the nodes will be the hyperlinks and each node of documents. So you can think of the internet as a graph that consists of how many, like trillions and billions and gazillions of documents, right? 그 노드가 이제 뭐 몇 쪽인지는 모르겠죠. 뭐 웹페이지라는 게 워낙 많으니까. And among those documents, among those nodes, which nodes are most the value of each node is determined by how many incoming links there are towards that document. So in hyperlinks in internet, the edges are directed, because it doesn't mean just because you have links to other document, that document doesn't have a link to you. It's directed when if you think about the hyperlink. So there can be outcoming links and incoming links, right? So if your certain web page, for example, like Naver's main web page or google.com or facebook.com, those kind of web page will have trillions and trillions of incoming links or incoming edges, because a lot of other pages will have links to facebook.com or google.com, right? So those pages are valuable, and the pages that do not have any incoming links are less valuable, or like has minimum value. So when you are ranking the documents based on the query, you would like to rank the high value documents on the top and low value documents at the bottom, basically. So you can see this is the like a subgraph of the internet. So there's web page B, web page C, web page E, web page A, web page D, and there's the edges are directed. And you can see that so the basic algorithm in PageRank is that you start from a random web page, and then you start taking random links for like a fixed amount of times, like fixed amount of hops. You hop around the internet web pages for like 100 times or maybe 200 times, like a fixed amount of time, and then the web pages that you visited randomly will have will get like a certain score. Like the more times you randomly visit a certain web page, that web page will have higher value, something like that, and then that becomes a rank for the search engine. All right, and these days chemical compounds are a big hit due to are using AI to develop drugs or find new drugs for cancer, that kind of stuff. So chemical structure are obviously graphically strong, are graphical. So each atom will be a node, and in this case, nodes have features, because node C is carbon, O is oxygen, H is hydrogen, N is nitrogen. So each node will have a certain identity, not just index, but also it'll have a class or identity. And then there can be different edge types as well. There's single bond and there's double bonds. So these, in this case, chemical compounds have multiple edge types. And hot topic these days because of the drug development or toxicity prediction. For example, like if you came up with a new drug chemical compound and you want to use them for certain purposes, like making drugs or making spices or whatever, and you want to predict whether the newly engineered chemical compound is toxic to people or not. In that case, you can use graph neural networks to do binary classification, given a graph, whether it's toxic or not. Right, and the next example is knowledge graphs, or knowledge base. So in this case, this is probably the most complexly structured data, or has the most complex nature among graphs. So there are multiple node types, there are multiple edge types, and there are obviously directions. So it has everything together. So in this case, multiple node types being, there are entity nodes and value nodes. So for example, here, if you look at this, there are specific nodes like Da Vinci or Mona Lisa, and there's an abstract node or entity nodes such as person or museum. So these person nodes or museum nodes or place nodes, they are entity nodes. So they don't have any meaning. It's just a type. And the Da Vinci or Lily, James, the Eiffel Tower, Paris, they are concrete entities. They have values. So in that case, oh, I'm sorry, it's the other way around. Actually, yeah, I described them in the reverse order. The ones that have concrete values are entity. These are entities. Da Vinci, Lily, Mona Lisa, James. They are entities. They exist in the world. So I'm sorry about that. And empty nodes like these, like museum, Lily is a person, or James was born in January 1st in 1984, or Paris is a place. Like these smaller circles are value nodes because they represent nothing but just a value. They, like museum or place, they don't exist in the world. They are like values or ideas. And obviously the edges are multi-type edges. So for example, here, James is a person. There's an is-a relation. Then there's like a Da Vinci painted Mona Lisa. There's painted relation. Is located in is another type of relation. So there are at least 4 or 5 types of relations. And this entire thing represents basically represents the common sense, like all the knowledge in the world, like a Wikipedia based. You can think of them as like a structured graphical knowledge base for Wikipedia. And yeah, and they are heavily used for knowledge grounded reasoning. For example, like if you ask questions such as, where is Mona Lisa located? So I should erase all this. So if you ask a question, where is Mona Lisa located? Then first of all, you have to find Mona Lisa in the knowledge graph, and there it is. And then you look at, and you find out that it is in Louvre, the Louvre 박물관이죠. It is in Louvre, and the Louvre is located in Paris. So by hopping by the rule of induction, Mona Lisa is located in Paris. So you can answer the question, where's Mona Lisa located? The answer is Paris. So that kind of inference questions can be done on top of this knowledge graph. There's a question. Okay, not a question. All right, moving on. So generally speaking, so we've taken a look at 4 or 5 examples of graphs, and generally speaking, everything is a graph, as I said. So sequences, for example, like a sentence that consists of sequence of words. Sequences are a special case of graphs because in sequence, for example, I am a boy, end of sentence. They form a sequence, and sequences where each node is connected to another node and only another node only. So for example, A is only connected to B, B is only connected to C, C, D, D to E. So they form a chain, and chain is called a sequence. In this case, it's just a very, very simple graph, and 2D images are also actually graphs. So images are also a special case of graphs. because and it's undirected. So in this case, it's directed because there's an order. Like A is position one is position 2, position 3, 4, 5. So in order to represent the positions, you have to have an arrow in the edges. So in this case, they are directed graphs or directed chains. But in images, usually you can think of them as undirectedly connected. So for example, this is a 4x4 resolution image, and each node is a pixel. So there will be a certain pixel value. If it's a grayscale image, it'll be a one-dimensional value. If it's an RGB image, then each pixel will have a three-dimensional value. And each pixel is connected to only at maximum 4 other pixels. For example, if you look at this, then it's only connected to top, left, right, bottom. So that's as far as connections go in 2D images. So they're connected, and so it's connected, and there is no, there's no direction or anything. It's just connection, and this is repeated across all images, all images. So you can think of them as 2D grids. So these are called chains or sequences, or sequences. The 2D images are called grids, right? So for example, so technically, if you know how to program graph neural networks, then you can use them for sequences or even images, because it's the same. They're all just special cases of graphs, right? All right, moving on to graph convolution. So, okay, question. For the multiple nodes and edges, are they predefined or learned feature tree? Okay, so the definition of the multi-type nodes and multi-type edges were already predefined in the examples that I've given so far. Right? Like in chemical compounds, we knew that they were multi-type nodes and multi-type edges because there were multiple types of nodes, like carbon nodes or hydrogen nodes or oxygen nodes, and we knew that there are multi-type edges because of the single bond and double bonds. So in this case, they are predefined. So you have to study your graph and then figure out what kind of node, what kind of graph we're looking at, and see if there are multiple types of nodes, multiple types of edges, and multiple types of we have to figure out the kind of knowledge by studying the data set. Great. All right, so graph convolution. So graph convolution, we need to do graph convolution because basically what we want, the whole idea behind neural networks is learning a representation of a given data set, right? So in this case, we want to represent a given graph we want to embed a graph into a fixed size vector most of the time. That's what we want. And how to do it, that's where graph neural network comes in. So for example, images can be represented by convnets, CNNs typically. So for example, resolution of 128 image with RGB color. We can feed this image into a ResNet, and then what we would get is a globally average pooled 2048 dimensional feature vector. So a 128 by 128 by 3-dimensional RGB channel. We can push it through a ResNet. So it's a ResNet, and then you would get a really long 2048 dimensional vector. So any image, any 128 image, given that, we can always transform or compress it or embed it into 2048 dimensional image. For example, text can be represented by RNNs or BERTs. For example, 20 token text, if you feed it through RNN or BERT, we'll get a 20 contextualized embeddings. So each contextualized embedding for each token. So we'll 20 token in, 20 contextualized embedding out. So images, we use convnets. Text, we can use RNNs or BERTs. So graphs, what do we use? So what do we want to get out of when we feed graphs into a certain neural networks? What do we want to get out of? For example, graphs consist of nodes and edges, right? And number of nodes, we're just going to use them as V, like bar V, and number of edges we're going to denote as bar E. So this number of nodes and this number of edges, graph that consists of this number of nodes and edges, where do we feed it into, and then what do we want to get out of? And this we still don't know. So the embedder or the encoder, we don't know, but at least we know what we want to get out of. We usually want to get v number of embeddings. So because there are v number of nodes, we want to at least get v number of embeddings, just like in the case of text, 20 tokens in, 20 contextualized embedding out. So same principle, v number of nodes in and v number of embeddings out. And so each embedding here will represent each node in the graph. And sometimes we would also want to obtain e number of embeddings for representing edges. So we not only want to represent each nodes, but we also want to represent each edges, like the entire edges in the graph. But this is usually we don't do that. Usually we don't care about the edges. We usually only care about the nodes. For example, if you want to classify a given certain node into certain classes, or if you want to, guess whether two nodes are connected or not. For example, like friends recommendation, that when you're doing friend recommendation, you take a couple of nodes that are not connected and then predict whether they should be connected or not. So in that case, all we need are also just two representations for those two nodes, right? So it's usually the node representations that we require for downstream tasks, and the edge representations, not so much. So we're gonna focus mostly on this. So why don't we use just convnet, for example, when we want to encode graphs, or when we want to obtain represent v number node representations? Why not just use convnet, for example? Because convolution filters assume same number. So because of this reason, convolutional filters assume same number of neighbors. For example, when there are 4x4 image grid, we can use 3x3 kernel, like 1, 2, 3, like 3x3 convolutional kernel and 3x3 convolution kernel, or whether it's 3x3 or 5x5 or 6x7x7, doesn't matter. They all assume same number of neighbors, which means that the maximum number of neighbors a single pixel can have is 4, as I said, because there are 1, 2, 3, 4 neighbors for this guy. But that is not the case, because in graph, like any arbitrary graph, the number of neighbors can change. For example, here this guy only has 1 neighbor, but here this guy has 1, 2, 3, 4, 5, 6, has 6 neighbors. So the number of neighbors can change for each node in arbitrary graph. So we can't use convnet. We can't use this kind of convolutional filters to move around the graph and collect the neighbor information. But essentially that is what convolutional filter does. Convolutional filter, given a single, given a main character or main pixel, it gathers the neighbor 1, 2, 3, 4, 5, 6, 7, 8, 8 neighbor pixels information, and then weight sum them together to produce a single scalar value, right? And then then the filter moves on to this guy, and then again gathers 1, 2, 3, 4, 5, 6, 7, 8, 9 pixel values, and then weight sum them, and then get another pixel, another scalar value, and then keep doing that, like sliding across the image, and then keep producing the scalar values, right? So that's what convnet filter does. Focusing on a single main pixel, and then gathering neighbor pixel values and weight summing them, and moving on to another main target, moving on to another main target, moving on to main target. Keep repeating this until you arrive at the end of the image, right? So we want to do a similar thing in graph neural networks. The problem is that we don't know, there is no fixed number of neighbors per node in graph, and also there is no order. For example, here, like this is the pixel number 1, this is the pixel number 16. So we go this way, right? But there in graph neural networks, there is no such order. But we can still assign random order, like this can be 1, 2, 3, 4, 5, 6, 7. We can do that, but still, this is a bit different than images. There's no up and down, there's no left and right in graphs, right? So that's the difference between grid images and graphs. But we can still, as I said, we can still use similar images. So we can use the core principle of convnet filter, which is aggregating features from the local neighbors. So we move, we move from one pixel to another, gathering neighbor information, weight summing them here, and then moving on to next pixel, next pixel, next pixel, next pixel, until we arrive at the end of the images. Arrive at the end of the image. Right. So following that principle, what we would do is, so given a graph that consists of a set of nodes and a set of edges, at each node vi, at ith node, aggregate all neighbors' features. So this is what we want. This is what we want. Like this, like here, we want to aggregate all neighbors' features. So this thing here, AI is the aggregate representation or aggregate information of all neighbor nodes of this ith node. So let me just make this a bit clear. So we are at ith node. So we're at ith node here. We're at ith node. So AI is the set of nodes connected to the ith node. So all the neighbors, all the nodes that are connected to the ith node, we take them and then we put those neighbor nodes into some function, and then we add those values. So that's this function, this FVJ will take a certain node and represent it and embed it into a fixed size vector. It could be 128 or some d-dimensional vector, basically. So it'll take a node and then turn that into a fixed size vector, and then we add them. There's a sigma here. We add all these d-dimensional vectors from all the other VK, VH. We add all of them, and this becomes AI here. This becomes AI here. So that's what neighbor aggregation is. So you take, so at the ith node, we take all the nodes that are connected to the ith node and then push and take each neighbor, feed them into a function, and then obtain a representation vector, and then we keep doing that for all neighbors, and then we add them together, and then we get the final aggregate vector AI. So that's the aggregation part. And then we need to combine the ith field, because this is all just neighbor aggregation. We still haven't combined that with the main target node, the ith node yet. So we have another function G that takes the neighbor aggregate representation and the main target, the ith vector, which should also go inside a function. So this will also become a representation vector of the ith node. That we somehow mix them together, combine them together using the function G, and then obtain the final representation H. So HI is the final representation vector of the ith node after aggregating the neighbors and combining the aggregate with the main of it with itself, and then HI becomes the representation of node VI. So this is what we want if we're following the principle of the convnet. No question here, right? It's pretty straightforward. I mean, in an abstract idea is pretty similar with convnet. And of course, we should do it for all nodes, because this is just at each node VI. So we should visit all nodes in our graph and then keep doing this, obtaining the the H representation for each node. All right. So graphically, let's take a look at them graphically. Let's assume that there is a graph that looks like this. So a graph that consists of 6 nodes and 1, 2, 3, 4, 5, 6. 6 nodes and 6 edges, actually. 6 nodes and 6 edges. And if you've studied data structure or algorithm, then you know what adjacency matrix is. Adjacency matrix is a way to represent a graph using a matrix, basically. So adjacency matrix here, this is an adjacency matrix. So because there are 6 nodes, so we have an index for each node. So this is node number 1, node number 2, number 3, 4, 5, 6, and this number doesn't mean anything. It's just an index, because we want to represent this graph as a adjacency matrix. And this first row corresponds to node 1, node 2, number 3, 4, 5, 6, and this value here represents which node each node is connected to. So this also, actually, the columns are 1, 2, 3, 4, 5, 6, and if node 1 is connected to node 2, like here, then it's 1. Node 1 is connected to node 3, so it's 1 here. Node 1 is not connected to 4, 5, 6, so it's all 0 here. And also it has no self connection either, so 0 here. So you can see what's happening. So node number 2 is connected to 1, 4, 5. So 1, 4, 5 is 1. All the others are 0. So basically that's it. So adjacency matrix is just a binary valued matrix where the number of rows and columns are the same as the number of nodes in the graph, and the value of each cell in the matrix corresponds to the connection, whether there's connection or not between a pair of nodes. Right. So this adjacency matrix is what we're going to use afterwards, explaining the graph convolution. So keeping this in mind, we denote the adjacency matrix as A, and we have a node, we have XW here, XW. So XW is what? It's just a embedding of each node. So VI, V2, V3. So V1, 2, 3, 4, 5, 6. There are 6 nodes. So V1, we push it through F, push it through F, and we push it through the same F, the function that encodes a node into a fixed size vector. So that's simply just using a lookup table, basically. X is the node index, and W is the lookup table. And it's the lookup table for nodes. So in text in NLP, there's lookup table for tokens, right? So here we have lookup tables for nodes. So simply XW is just, will give you a fixed size vector for each node, and that's it. So we have A, X, and W. What happens if we just simply multiply them? We have just, matrix multiplication between A and XW. What happens? Then you take this row and take this entire thing, you do an inner product, and then you obtain this, right? So because 1, 1, so all the others are 0, and only the second and third columns are 1. So only the second and third row will be alive in here. If we look at the second row, then only the first and fourth and fifth columns are non-zero. So we take first and fourth and fifth, and then get this here, right? So we keep doing that for all rows, or all rows here, actually, all rows here. And then that's what we get when we do AXW. So far, what have we done here? By multiplying A and XW, the adjacency matrix and the node features or node embeddings, multiplying them, what did you get? We got for each row, for each node, for example, this still represents node number 1. This still represents node number 3, 4, 5, and 6, right? So for node number 1, what we did is we aggregated the neighbor features, because what we wanted to do here was aggregate. So I'm going to erase all of this. Sorry. So here, what we want to do is we want to add all the neighbor nodes feature vector. That is neighbor aggregation, right? So that's what we've done here. Neighbor aggregation. 1 is connected to 2 and 3, so we have neighbor aggregation done. For 2, 1, 4, 5, they are the neighbors, and we want to add all of them. So we did that here. So on and so forth. The AXW, that's neighbor aggregation. Moving on. Is this the node representation? So did we arrive at the end? Do we have the HI for each VI? Do we have this? Actually, no, because we just aggregated the neighbors, and we haven't combined the neighbors with itself. So if you remember here, there's the aggregation step, and then there's the combination step. Combination being using the aggregate embedding and itself, and somehow, combining them together using another function G. That is how we finally obtain the H, the final representation of each node. So we need to. So far we have only done neighbor aggregation. We haven't done the combination step. So we do need the combination step here. So how do we do that? So we simply just add the value 1 across the diagonal section of the adjacency matrix. So here, if you look at the adjacency matrix, we fill the diagonal cells with 1 and see what happens if we do this. So we're gonna call this A prime. So A is the adjacency matrix, and I is the identity matrix. So if we add them, so this thing is simply a summation between A and I, right? So we're going to call this A prime. So what happens if when we do A prime XW. Then we have a self connection. So 1 is now connected to 1. 2 is connected to 2. 3 connected to 3. So what we have is we simply added a self loop here, like the self connection here, self connection. And when we have this and do A prime XW, then we have it's the self embedding involved in the final summation. So there's neighbor aggregation here, and you're adding that with self embedding. There's neighbor aggregation here, and then you're adding the self embedding. Again, the same deal with here, here, and here, right? So neighbor aggregation plus the self embedding by simply doing A prime XW. So that's how we combine that. I mean, the combination is a bit straightforward. What we did is simply we just added all of them together. So it's not much of a combination, right? It's just summation, but still we have now everything we need to call each of them as H1, H2, H3, H4, H5, H5, right? H1, yeah. There is still, I mean, the combination function G is simple summation in this case, so it's not much, but you can expand them using like multilayer perceptron instead of just summation. You can concatenate HV1 and these two. So they will be a summed embedding, but you can concatenate the summed embedding and the self embedding, and then somehow push them into a neural network to obtain H1. That's up to you. But in this example, we're gonna just stick with the summation example. So are we finally done? Are we finally done with the H? Not so much, actually, not so much. The problem, there's still a caveat. So the problem is that because each node has different number of neighbors connected to itself, there can be some magnitude difference between H's. For example, H2 can be twice as large as H5. What does that mean? So H2 is a summation of 4 node embeddings. H5 is summation of 2 node embeddings. Why is that? Because 2 is connected to 1, 2, 3 three neighbors, and counting the self connection as well, then you have 4 summations. 5 on the other end, node number 5 on the other end is only connected to 2, and counting the self connection as well, it's only connected to two neighbors. So this summation with 4 embeddings versus summation with 2 embeddings. So there can be some magnitude difference or the norm difference, because we're using the vector representation here, H2 and H5. They're vectors. So their vector norm values might be significantly different. So we need to somehow deal with that. So what we need is a normalization step. So normalization step being, we just simply divide each row of the adjacency matrix based on how many non-zero values there are. So here there were 3 non-zero values. So we simply just divide the first row with, divide the first row with 3. So it's just a third of 1/3, 1/3, 1/3. Here there were 4 non-zero values. So we divide the second row with 4. So we have a fourth, a fourth, a fourth, a fourth. The same deal with here and here. Here there were only 2 non-zeros. So we divide by 2. So there's a half and a half, and that's it. So when you do this, then we call this now D inverse A prime. So A prime was A plus I, right? Now D inverse is simply just it's just a normalizer. So D inverse is actually looks like a 1/3 here, 1/4 here, and 1/4 here, 1/3 here, a half and a half. So D is actually a degree matrix, a diagonal matrix where each diagonal cell is number of edges, and D inverse is a flip of that. It's an inverse of that. So D inverse would look like this exactly here. So when you multiply D inverse with A prime, then you would get this guy, right? You get this guy. And then so finally, when you do D inverse A prime XW, then we have the final normalized H's for each node. So each HI for the ith vector, right? And then, yeah, last but not least, we need actually a nonlinear activation function, because after all, we're dealing with neural networks, right? So we need a nonlinear activation function somewhere, and we're going to put that after D inverse A prime XW. So the final representation H, actually HI for V, HI from VI go, actually, yeah, this is actually a bad notation. So given GNN, some function GNN, given VI, we arrive at HI. This whole thing is including the nonlinear activation function. It'll be D inverse A prime XW, right? So this is the same thing. And in a very naive form of GNN, this is the simplest, like the simplest, most straightforward graph neural networks. So it's a pretty straightforward algorithm, right? Because a single graph convolution step consists of only one learnable parameter. I mean, there is how many? What's the learnable parameter here? Among all the alphabets and all the nonlinear activation function, there's only one learnable parameter, which is the lookup table, and that's it. D inverse is given based on the degree of neighbors. A prime is given based on this architecture or the topology of the graph. X is given as an index of each node. W is the only learnable parameter, which serves as a lookup table for the nodes, and that's it. So it's a very, very simple network. It's a very lightweight network, actually. Right. So yeah, this is the final notation. So H being like a group, just a group, set of node embeddings, set of node embeddings after the graph convolution. So all the H's, H1, H2, H3, all combined is called H, and H is derived by this simple algorithm. Nonlinear activation with D inverse A prime XW. Right. So graphically, what happens is that when you have a raw graph and then you do a single step of graph convolution, we're going to call this H1, a single step. We did we put the x's into this function one time, so we get H1, and we are simply what happens is that now this, if we look at here, each row still represents each node, like 1, 2, 3, 4, 5, 6. Now 1 from here, 2 from here. So what happens is that now each node is no longer itself. Like before here, like here's if we started from here, started from here and then we arrived here. So before, each node was just itself, but now each node is actually a combination of itself and its neighbors. So now it's a bit modified. So you can think of this as a modified identity now. Before it was just itself, it was just pure 2, pure 3, pure 4, 5, 6. But now after a single graph convolution step, now each node is a bit of a mix between itself 1 and its neighbors 2, 3. Mix between itself and the neighbors, mix between itself and its neighbors. So now they're a bit tainted or they're a bit modified. So that's what happens. And what we did is aggregating neighbor just one hop away, like direct neighbors. Now 1 has become 1, 2, 3, and 2, 3 is the one hop away. 2 has become 2, 1, 4, 5, and 1, 4, 5 was one hop away, right? So what happens? What do we do if we want to aggregate neighbors from two hops away? So simple. Following this equation, we were able to aggregate neighbors from one hop away. But what do we do if we want to aggregate neighbors from 2 hops away? The question, the answer is pretty simple, actually. What we do is we just simply do another graph convolution. So before we had D inverse A prime XW, but since we want to do we want to aggregate neighbors from 2 hops away, we take the H1, plug that in here, and then do the same thing. D inverse A prime H1 and W2 now. We need another learnable parameter because it's now another graph convolution. So we need H1 as an input and W2 as a learnable parameter, another learnable parameter. And then what happens? Then we get H2, which now is a representation that aggregates neighbors from 2 hops away. So if we take a look at here, what happens if we do another graph convolution with this graph here, with this modified graph? Then what it would do is starting from here and doing a single graph convolution. Then for this guy would aggregate information from 1 hop away, which is 2. So this happens. So 5 plus 2 is now itself. 5 plus 2 is the self. So it retains itself. And then what is one hop away? Only this guy is one hop away. So now we have this aggregation here. So in effect, overall, if you look at the values here, it's 5, 2, 1, 4. 5, 2, 1, 4. It all consists of 5, 2, 1, 4. And 5 is itself, and 2 is one hop away, but 1 and 4 are 2 hops away. So 5 and 2 are one hop away, but 1, 2. 1 is 2 hops away from 5. 4 is 1, 2 hops away from 5. So that is why we have 5, 2, 1, 4 after another graph convolution step. So as we repeat the graph convolution steps, we are actually collecting information from n neighbors that are n hops away. If we do n graph convolution, then we're collecting information from neighbors that are n hops away. So yeah, how do we aggregate neighbors from k hops away? We simply do graph convolution k times. So in that case, we would need learnable parameter W1, W2, all the way to WK. So you can think of this as just, stacking the layers of graph convolution. Just like stacking the transformer layers, we're stacking graph convolution layers. We're repeating the graph convolution layers, and each layer requires only one learnable parameter, which are W. I mean, we're forgetting about the bias term, so there can be bias term somewhere, but mainly we're dealing with the learnable matrix W, and each layer of graph convolution requires one learnable lookup matrix, and that's it. Right. There are a lot of variations. I mean, there are graph convolution neural networks was proposed back in 2016. I'm not really sure. It's a really long time ago now by today's standards. So after graph convolution, the original paper, a lot of variations has poured out, and there are different flavors. Like, for example, different normalization schemes. So what we did is the inverse A prime XW, but there's another way to normalize the adjacency matrix, which is using the half inverse and half inverse, multiplying side by side, multiplying before and after the adjacency matrix. And yeah, this is motivated by spectral graph convolution theory. And so there's a whole theory behind graph Laplacian matrix and all that. So if you're interested in that, you can look them up. So this is like the authors claim that this is a better normalization than simply just multiplying AD inverse here. And different combination step as well. So far, what we did is we simply summed the self-embedding with the neighbor embedding, which was G was simply just a summation. But as I said, you can do linear layer, like you can have a concatenation between self-embedding and the neighbor embedding, and then put it through a nonlinear activation function, or maybe several layers of feed-forward network. That's up to you. So different combination steps, and sometimes nodes can become RNNs. For example, like it's a more sophisticated way to accumulate n-hop information. When you aggregate information by stacking the graph convolution layers, you can actually chain each node by using LSTM. So, for example, there are a lot of many word variations, and they're all called, as a family, they're all called graph neural networks. But the ones that we studied today is like the simplest, like most straightforward version of graph neural networks. All right, any questions so far? Question from MJ. When X is replaced with H, do the X and H have the same shape? Shape, oh, you mean the same dimensionality? Doesn't have to be. So because it all depends on W. So when we start with D inverse A prime XW, X being R, for example, R128, and there should be H1. For example, if you want H1 to be R256, then simply what you need to do is you just need to have W that has R128 to 256. If H2 D inverse A prime H1 W2, in this case, H1 is 256, and if you want H2 to be R 512, then you can simply dictate that W2 should be R256, 512, right? It's all up to you. Hopefully that answers the question. Question from Wuhan. So are there large scale pre-trained node embedding like Word2Vec in NLP? If not, what's the reason of not making those kind of pre-trained? Interesting question. So the utility of pre-trained Word2Vec comes from the fact that words are the unit, are the like the, how do I put this? It's the Word2Vec in NLP. So actually Word2Vec is a kind of outdated concept, but still, if we don't think about the subword embeddings, if we think about the old days where words were the unit, it was the basic unit of information unit of all in NLP. Like for example, if you're at least dealing with English literature, I don't, so Jisoo, I don't think that's what Wanzog is asking for. Deep walk or Node2Vec is an algorithm. But I think what Wanzog is asking for is there any pre-trained vectors for graphs? And the reason there is no pre-trained vectors for graph, at least that depends. But so as I was saying, Word2Vec in NLP has utility because words are in basic information unit in dealing with all English NLP, because English NLP is all based on words. So that is why you can, if you have pre-trained word embeddings, you can use them for any downstream task, for document classification, translation, chatbot, whatever, sentiment classification, whatever. But graphs, it depends. So there aren't many. It's different like NLP. It's like, you know, it's not like there's information unit for graphs. Like if you're dealing with Facebook, then you can have pre-trained node embeddings for Facebook friend, Facebook user embeddings, but you can't use them for other graphs, right? It's only useful for Facebook friends. If you have like a atom pre-trained embeddings for atoms, for chemical compounds, you can use those pre-trained embeddings for toxicity classification or, you know, developing drugs, but you can't use them for other graphs. So there is limited utility. But Word2Vec has a lot of utility because all NLP is based on words. Hopefully that answers the question. Question from Yusun Wu. We need several stacking layers to effectively propagate messages. However, there are a number of layers. As a number of layers, oversmoothing happens. How to bypass this right now? Yeah, graph pre-training is an algorithm. So we can have algorithm for pre-training, but the question was from Wuhanza was, why isn't there pre-trained embeddings uploaded on GitHub or like Hugging Face, as far as I understand. So pre-training algorithms can be still developed and proposed because they're useful, but the actual pre-trained embeddings, I don't think there are a lot of people are doing that. And overstacking. So overstacking is an important concept. If you, as I said here, if you stack k number of convolution layers, then you are aggregating information from k hops away. And if you do it for example, let's assume that you have this graph that we took, actually, yeah. So in this example here, if we stack, if we stack for example, 4 layers of graph convolution, then a single node can take a look at, a single node can collect information from all other nodes, because I think no other nodes are at least, no pair of nodes are 5 hops away here. It's 1, 2, 1, 2, 1, 2, 3, 1, 2, 1, 2, 3, 4. Yeah. So yeah, I think in this node, the maximum number of hops away are 4 hops away. So if you stack 4 convolution layers, then any given node, any arbitrary node will be able to collect information from all other nodes. So that means that it no longer is like the structure of the graph is no longer really useful. It's no longer effective because the whole idea behind graph neural networks is that you want to collect information from your local neighbors. So maybe 1 hop away, 2 hops away, maybe even maybe 3 hops away. But if you stack the graph convolution layers, like maybe like 100, if you stack them 100 layers, then you're actually aggregating information from 100 hops away, and it's no longer local information. It's as good as global information. So that there's like there can be like a magic number, like how many layers you want to stack, how many layers you want to use in your graph convolution without actually, overshooting your target, without going global. So usually that number is 2 or 3 in my experience. People don't stack like 5 or 6 or 7 layers of convolution stacks when they're dealing with graphs, because that's actually, you're starting to go global rather than local. So you just have to limit the number of stacks, limit the number of layers you stack. Usually it's just 3 or more or less. Yeah. Hopefully that answers the question. I mean, there will be some papers that tries to circumvent that the problem. So using slightly different adjacency matrix per layer, or maybe using residual networks between layers and all those things. But in principle, if you want to stick to local information, you can just stack smaller number of layers. Right, moving on to the GNN and transformers. There are a lot of questions. Good sign. So yeah, not specifically graph convolution versus self-attention. So self-attention, it's just a simple recap. So given a sentence like this, I like going to movies, end of sentence. The assumption behind self-attention is that all words or all tokens in a sentence is related to all other tokens. So I forgot the self loop here, but all tokens are related to other tokens somehow, and we don't know how related or how strong the relations are. So we turn to attention to determine the strength of the relationship between a pair of nodes. But basically, the idea behind it, the premise underlying the self-attention is that everything is connected to everything else. So for example, like there's I like going to movies and end. So it's fully connected graph. If you study graph theory, then it's fully connected graph. Like it's like everything is connected to everything else. Everything is connected to everything else. Like here, here, here. Yep. With direction, actually. It's with direction because there's direction here, right? So with direction. So it's completely connected, and it's just a matter of the strength of the relation, strength of the edge. So there's edge here, there's edge here, edge here, edge here, edge here. And we don't know how strong the edges are, but so that's determined by the attention mechanism, right? But basically it's all connected. So compare. So if you think of the QKV operation, this is a bit extreme because there are 0 weight edges, and this should be 2 actually. 0 weight edges, but typically when you apply attention mechanisms, there is no absolute 0 edges. Actually, they'll have like minimum values like 0.001 or something. But still, anyway, so QKV operation, this much was the attention map. So this was the attention map, and this V was the token embeddings, and then you multiply them. You do matrix multiplication between the softmax output and the V embeddings, and then you obtain this, which is just the weight sum of the node embeddings based on the attention strength, right? So if you compare this with graph convolution, here it's exactly the same shape. So there's attention map here, but there's normalized adjacency map here. And they both are normalized because row-wise, if you do summation row-wise, then it should sum up to 1 because it's a probability. Sum up row-wise, it should be 1. So that's why I said it should be 2. Sum up row-wise, it should be 1. Same deal here. Sum up row-wise, it'll be 1. Sum up row-wise is 1, 1, because we've normalized based on the number of neighbors connected to each node, right? So there's a 1-to-1 comparison. So the softmax QK is exactly the same shape as this. XW is the node embedding. So this is the token embedding, this is the node embedding, right? And then you do multiplication between the two, multiplication between the two, multiplication between the two, then you get the weighted sum, weighted sum. It's just that in self-attention, the structure of the graph or the attention or this map, adjacency map, is determined by strength, determined by the attention mechanism. It's not determined by the data. It's not determined by the people, not the user. It's determined solely based on the learnable functions of the attention mechanism, self-attention. Here, this adjacency map is predefined. It's defined by the data. So that's the only difference between the two. And yeah, the weight summing effect is the same. So yeah, if you look at the graph network, so now we have the D inverse A prime XW, but now we just call them C. So CW, and then instead of having a single nonlinear activation function, we have an MLP, like to increase the power. So this is a general form of graph neural network. Transformer, if you forget about the norm, if you forget about the add-in norm, like residual connection and the layer norm, it can be looked at it like this. So there's a softmax QKV operation followed by a feed-forward network, right? If you look at the encoder of the transformer, there's self-attention, there's add-in norm, there's feed-forward, there's add-in norm. But if you forget about the add-in norm, it's just self-attention followed by a feed-forward network like this here. So if you think about these two, there's a one-to-one correspondence between the adjacency matrix and softmax part, which is adjacency matrix and self-attention. And then CW, the node embedding, is the same as V, which is the node token embedding here. It's the same thing here. So there's two more learnable parameters in self-attention, which are WQ and WK. The Q query generating matrix and the key generating matrix, but the value generating matrix is the same as node lookup matrix, right? So there's a clear parallel comparison between the two. So all in all, self-attention, you can use them when you know that the given data is graphically structured. You know there's a relationship between the tokens or the nodes. You know there's a relationship, but you don't know the structure or the topology of the graph. So that's when you rely on attention. So you don't know the graph structure, but you assume that it's fully connected, and then learn edge weights during training. So during training, you hope that the graph structure, the graph topology will be learned using the attention mechanism. And the node embeddings. So basically what you're doing is learning the node embeddings, V number of node embeddings, in a purely data-driven fashion. Graph convolution, on the other end, you have a prior knowledge of the graph structure. So that is reflected on your adjacency matrix. So prior knowledge of graph structure is reflected on your D inverse A prime, right? So learn node embeddings based on the fixed adjacency matrix. So based on the data, you know the topology of the graph, and then you can simply reuse them at each layer to derive or obtain the node embeddings, the V number of node embeddings. So that's the relationship between the two. So when you're dealing with a graph, if you know the structure, you can use transform. If you know the structure, you can use graph convolution. If you don't know the structure, you can use self-attention. And if you know a partial structure of the graph, then you can use a hybrid version of that. Maybe you can, do we have graph attention? Yeah, we have actually graph attention network. So so there's a paper called Graph Attention Network here. Very popular network, like baseline graph, very popular go-to method for dealing with graph. It's learning the edge weights with attention. So you do know which nodes are connected to which other nodes. So you know the graph topology. And if you think about this here, if you think about the adjacency matrix here, which is the one that we use, all edges have exactly the same weight. But sometimes we don't want this. We probably want some edges to have higher weights compared to than some other edges, right? In that case, we can use attention on top of these live edges only. So for example, what we can do is if you remember the negative infinity mask matrix from the transformer class, we can use the mask matrix, or is it mask matrix? Yeah, basically we can use negative infinity masks to mask out this part and then only use attention on this part, only use attention on these four, only use attention on these four, only use attention on these two, attention on these two, I'm sorry, these three, these two, in order to dynamically learn the edge weights based on attention, only for live edges, only for connected edges. All the other edges, like the zeros here, they wouldn't get any attention anyway. So that's the idea behind graph attention networks. So it's a bit more flexible than fixed edge weight, than graph neural networks with fixed edge weights, right? So that's yeah, here you can have mask QK square root D with negative infinity matrix, and yeah. So you can have like a hybrid, you can mix the self-attention graph neural networks to your satisfaction. You can come up with clever ways to mix the idea from those two worlds, and then somehow come up with a better algorithm to deal with partially with with data where the partial graph structure, or you know the graph structure, but you want to have dynamic weights, something like that, basically. Right. So one last recent example are AlphaFold from DeepMind and some AI-based drug recommendation for COVID-19. So AlphaFold 2 is a more recent algorithm, but there was before AlphaFold 2, there's AlphaFold 1, obviously. So but those two have the exact same objective. Given a sequence of amino acids, they want to figure out the 3D structure of a protein. So a protein consists of amino acids, and a single amino acids form a sequence of amino acids. So there's a sequence of amino acids. Like in the human body, there are 20 amino acids, 20 amino acids. So it's like a text where only there are 20 vocabs, and they form a sequence. And this sequence, so a protein is basically a sequence of amino acids, and they form a structure, like a 3D structure. They don't, because of all they're like electromagnetic forces and whatnot, and van der Waals force and whatnot. They form a structure for like a helix structure, like 이렇게 꼬여 있는 거죠. Helix structure, or like a pleated sheet structure, like a 판상 구조나 뭐 이런 걸 만들죠. So there's a secondary structure, and then these form a third structure, a tertiary structure, which is in a 3D. Because we live in a 3D world, they form a 3D structure. So these 3D structure, so it's not just, so if you analyze a protein, then you can easily tell their sequence of amino acids, but it's really extremely difficult to tell how they're structured in a 3D world. And this is the important information, because when a protein interacts with another protein, like for example, if some drug interacts with some disease, or if drug interacts with some cancer cells, for example, it's all based on protein 3D interaction. So you want to know the 3D structure in order to develop drugs, or whatever that happens in our body. It's always proteins interacting in the 3D world. But it's rather easy to figure out the sequence of amino acids given the protein, but it's hard to figure out how the amino acids are located geometrically in the 3D world. So before, what people did is they took the protein and then taken like an X-ray image of a protein, and then try to figure out how they're shaped in the 3D, how they're 3D shaped. But it takes a lot of time, takes a lot of money. But what a lot of people try to do is they try to guess, given a sequence of amino acids, they wanted to guess the 3D coordinates of each amino acids in the 3D plane. And that's what AlphaFold does. So basically, using a transformer, so they use something called evoformer, which is they use something called evoformer, which is a variant of transformer. So which is basically using self-attention, by the way. So using self-attention, they only accept a sequence of amino acids and then try to guess the 3D coordinates of each node. So it's a self-attention. So you have, for example, if you put 100 amino acid sequence, 100 token amino acid sequence, then you will have 100 contextualized embeddings for each amino acid, and then based on that, you can guess the 3D coordinates of each amino acid, right? So basically, that's what they're doing with AlphaFold version 1 and AlphaFold version 2. They put a lot of domain knowledge as well, but still, basically there is a lot of reliance on self-attention as well. So this is a great example of how transformer can be used to interact, how a transformer or self-attention can be used to guess the 3D structure or the graphical structure of 3D graph. COVID-19 as well. So when COVID-19 first came out, a lot of people tried to guess what kind of drug would be like the most effective against COVID-19 based on the similarity between COVID-19 and the MERS and SARS. They all are crown-shaped, so that's why there's called coronavirus. So given a COVID-19 structure, what people did is they took a lot of chemical compounds, like drug compounds, and then fed that into a transformer. So these are all drug compounds, so they're all chemical compounds. They should have actually a 3D. They should have a 3D shape or graphical shape, but instead of pushing them into graph neural networks, what they did is they simply just pushed them into BERT, and then try to do mask language modeling using, just masking out these single tokens like O and parentheses and double bonds and single bonds and all that, and then use a pre-trained BERTs to figure out whether a given sequence, given not graph structure, but given a sequence of these chemical compound would be effective to COVID-19 or not. And if you see here, the second most predicted effective drug was remdesivir, which was like a thing back in 2020, right? If you remember what remdesivir was. So it was a very effective, even though no graphical information was given, they could still figure, the BERT was still able to figure out the effectiveness of the drugs against COVID-19. So you can still see like if you have like tons of data, you can probably replace a lot of graph neural networks with self-attention, actually, because if you have infinite amount of data, theoretically. That's the lesson here. All right, so I think we're done today. I think we have a bit of a time. If you have any question, please shoot. And oh, by the way, so the specs of project number 2 would be announced on Classum on this Thursday. So please stay tuned. And yeah, that's it. And yeah, if you don't have any questions, you're free to leave. If you have a question, please shoot them now, or you can ask them. You can post them on Classroom. Yeah, I'm gonna wait about 10 seconds. All right, I guess then there are no questions. I'll see you guys this Thursday. This Thursday, we're going to implement graph neural networks, obviously, and then try to use small size data set to do node classification tasks. All right, see you guys this Thursday. Bye-bye.